What if everything we see, touch, and know is just the tip of an unimaginable cosmic iceberg? What if the universe is governed by forces so mysterious, so elusive, that they defy our understanding of reality itself? Today, we're diving into the unknown to explore 25 of the most enigmatic forces that shape the cosmos. From the invisible grip of dark matter to the mind-bending possibilities of the multiverse, these forces challenge everything we think we know about the universe. Together, we'll unravel the science, the mystery, and the cosmic intrigue behind these phenomena. By the end of this journey, you'll not only gain a deeper understanding of the universe, but also be left questioning the very fabric of reality. So, are you ready to uncover the secrets that control the cosmos? Let's begin. Now, let's turn our attention to the first and perhaps most perplexing force on our list, dark matter. Imagine looking up at the night sky and seeing countless stars, galaxies, and cosmic wonders. But what if I told you that everything we can see makes up only a tiny fraction of the universe? The rest, a staggering 85% of all matter, is something we can't see, touch, or directly detect. This invisible force is dark matter, and it's the cosmic glue holding galaxies together. Without it, stars would fly apart, and the universe as we know it wouldn't exist. So, how do we know dark matter is even there if we can't see it? Scientists have observed its effects through gravity. When they study the way galaxies rotate, they notice something strange. The outer edges move just as fast as the inner parts. According to the laws of physics, this shouldn't happen unless there's a massive amount of invisible matter exerting a gravitational pull. That's where dark matter comes in. It's like an unseen hand shaping the cosmos from the shadows. Yet, despite decades of research, dark matter remains one of the greatest mysteries in astrophysics. We know it's there, but we don't know what it's made of. Is it a new kind of particle, a hidden dimension, or something entirely beyond our current understanding? The search for answers continues, with experiments deep underground and in space aiming to catch even the faintest hint of this elusive force. Dark matter challenges our understanding of the universe, reminding us that there's so much more to discover. And as we move forward, this invisible enigma will continue to shape not only galaxies but also our quest to uncover the secrets of the cosmos. Next, we'll explore another mysterious force that's pushing the universe apart, dark energy. Now, let's shift our gaze to another cosmic mystery that's reshaping our understanding of the universe, dark energy. While dark matter holds galaxies together, dark energy is doing something entirely different. It's pushing the universe apart at an ever-increasing speed. Imagine the universe as a balloon being inflated, but instead of slowing down, the expansion is speeding up. That's the strange and counterintuitive effect of dark energy. The story of dark energy's discovery begins in the late 1990s, when astronomers were studying distant supernovae, the explosive deaths of massive stars. They expected to find that the universe's expansion was slowing down due to gravity, but what they found was the opposite. These supernovae were farther away than they should have been, indicating that the universe wasn't just expanding, it was accelerating. This shocking revelation earned the researchers the Nobel Prize in Physics and introduced the world to dark energy, a force that makes up about 68% of the universe's total energy. But what exactly is dark energy? That's where things get even more puzzling. Unlike dark matter, which exerts a gravitational pull, dark energy seems to work against gravity, acting as a kind of repulsive force. One leading theory suggests it's a property of space itself, often referred to as the cosmological constant, an idea first proposed by Albert Einstein. Another possibility is that it's a dynamic field that changes over time, known as quintessence. Yet, despite decades of research, dark energy remains as mysterious as ever, defying our attempts to fully understand it. This enigmatic force doesn't just challenge our understanding of physics. it raises profound questions about the ultimate fate of the universe. If dark energy continues to dominate, the universe could keep expanding forever, leading to a cold, dark, and empty future known as the Big Freeze. On the other hand, if dark energy's behavior changes, it could lead to entirely different scenarios like the Big Rip, where galaxies, stars, and even atoms are torn apart. Dark energy reminds us that the universe is far stranger and more complex than we ever imagined. As we continue to explore this mysterious force, we're not just uncovering the secrets of the cosmos, we're also redefining our place within it. Next, we'll dive into the mind-bending world of black holes, where gravity becomes so intense that not even light can escape. Now, let's venture into one of the most fascinating and terrifying phenomena in the universe: black holes. These cosmic giants are regions of space where gravity is so intense that nothing, not even light, can escape their grasp. They are the ultimate cosmic vacuum cleaners, devouring everything that comes too close, and yet they play a crucial role in shaping the universe as we know it. Black holes form in the aftermath of massive stars. When a star many times larger than our Sun exhausts its nuclear fuel, it can no longer support itself against its own gravity. The star collapses in on itself, triggering a supernova explosion. What remains is an incredibly dense core, so compact that it warps the fabric of space-time itself. This is the birth of a black hole. The gravitational pull of a black hole is so strong that it creates a boundary called the event horizon. Once anything crosses this point, there's no turning back. It's like a one-way door into oblivion. But black holes aren't just destructive, they're also cosmic architects. At the center of nearly every large galaxy, including our own Milky Way, lies a supermassive black hole. These colossal entities, millions or even billions of times more massive than the Sun, influence the motion of stars and gas around them, helping to shape the structure of entire galaxies. One of the most mind-bending aspects of black holes is how they distort space-time. Imagine placing a heavy ball on a stretched rubber sheet. It creates a deep indentation. A black hole does something similar, but on a cosmic scale. It bends the very fabric of the universe, twisting time and space in ways that challenge our understanding of physics. Near a black hole, time slows down, a phenomenon known as time dilation. If you were to watch someone fall into a black hole, they would appear to slow down and eventually freeze at the event horizon, even though, from their perspective, they would pass through it in an instant. Black holes also play a key role in some of the most energetic events in the universe. When two black holes collide, they send ripples through space-time called gravitational waves, which were first detected in 2015. These collisions release more energy than all the stars in the universe combined, offering us a glimpse into the extreme forces at work in the cosmos. Despite their fearsome reputation, black holes are essential to the universe's evolution. They help regulate the growth of galaxies, influence the distribution of matter, and even provide clues about the nature of space-time itself. As we continue to study these enigmatic objects, we're not just uncovering the secrets of black holes, we're also gaining deeper insights into the very fabric of reality. Next, we'll explore the strange and fascinating world of quantum entanglement, where particles can be connected across vast distances in ways that defy our everyday understanding of physics. Now, let's shift our focus to one of the most baffling and intriguing phenomena in the universe: quantum entanglement. Imagine two particles separated by vast distances, perhaps even light years apart, yet somehow they remain deeply connected. What happens to one instantly affects the other, no matter how far apart they are. This strange connection, which Albert Einstein famously called spooky action at a distance, challenges everything we think we know about space, time, and reality itself. Quantum entanglement occurs when particles, such as electrons or photons, become linked in such a way that their properties are intertwined. If you measure one particle's spin, position, or momentum, the other particle's corresponding property is instantly determined, even if it's on the other side of the universe. This connection defies the speed of light, which, according to Einstein's theory of relativity, is the universe's speed limit. So how can particles communicate faster than light? The answer lies in the bizarre rules of quantum mechanics, where the ordinary laws of physics don't always apply. This phenomenon isn't just a theoretical curiosity, it has profound implications for our understanding of reality. For one, it suggests that the universe might be far more interconnected than we ever imagined. Space and time, which we perceive as separate and absolute, might instead be part of a deeper, more unified fabric. Quantum entanglement also raises questions about the nature of information and how it's shared across the cosmos. Could this strange connection be a fundamental feature of the universe, shaping its structure in ways we're only beginning to understand? Scientists have conducted numerous experiments to test quantum entanglement, and the results consistently confirm its existence. In fact, this phenomenon is already being harnessed in cutting-edge technologies like quantum computing and quantum cryptography. These fields rely on the unique properties of entangled particles to perform calculations and secure communications in ways that were once thought impossible. But perhaps the most mind-bending aspect of quantum entanglement is what it tells us about the nature of reality itself. Some physicists speculate that entanglement might be a clue to a deeper, hidden layer of the universe, one where the distinctions between particles, space, and time blur into something entirely new. Could this phenomenon be a glimpse into the underlying structure of the cosmos, or even a hint that the universe is fundamentally interconnected in ways we can't yet comprehend? As we continue to explore the mysteries of quantum entanglement, we're not just uncovering the secrets of particles, we're also challenging our most basic assumptions about how the universe works. Next, we'll dive into the concept of cosmic inflation, the rapid expansion of the universe moments after the Big Bang, and how it might hold the key to understanding the cosmos on the largest scales. Now let's journey back to the very beginning of the universe, to a moment so brief yet so transformative that it shaped everything we see today. This brings us to the concept of cosmic inflation, a theory that describes the universe's explosive expansion in the first fraction of a second after the Big Bang. Picture this: the entire cosmos, smaller than a single atom, suddenly stretching out faster than the speed of light, doubling in size over and over again in an unimaginably short span of time. This wasn't just any expansion, it was a rapid, exponential growth spurt that laid the foundation for the universe as we know it. Cosmic inflation solves some of the biggest puzzles in cosmology. For instance, why does the universe look so uniform in every direction? No matter where we look, the cosmic microwave background, the afterglow of the Big Bang, shows an almost identical temperature. Without inflation, this uniformity would be nearly impossible to explain. The theory suggests that the universe started out so small and dense that it was able to reach a uniform state before rapidly expanding, smoothing out any irregularities. Another mystery inflation helps explain is the flatness of the universe. Observations show that space-time is remarkably flat on large scales, meaning it doesn't curve back on itself like a sphere or stretch outward like a saddle. Inflation stretches the universe so much that any initial curvature becomes negligible, leaving us with the flat cosmos we observe today. It's like taking a tiny, wrinkled piece of paper and stretching it out until all the creases disappear. But cosmic inflation isn't just about solving old puzzles, it also opens up new questions. What caused this rapid expansion? Scientists propose that a mysterious form of energy, often called the inflaton field, drove this process. This field would have acted like a cosmic engine, pushing the universe to expand at an incredible rate before eventually fading away, leaving behind the slower, steady expansion we see today. Yet, the nature of this inflaton field remains one of the biggest mysteries in modern physics. the evidence for cosmic inflation comes from subtle patterns in the cosmic microwave background, tiny ripples that serve as a snapshot of the early universe. These ripples are thought to be the seeds of all the structures we see today: galaxies, stars, and even planets. Without inflation, these structures might never have formed. But while the theory is widely accepted, it's not without its challenges. Some scientists argue that inflation predicts an infinite number of possible universes, making it difficult to test definitively. Others are searching for new ways to probe this early epoch, hoping to find clues in gravitational waves or other cosmic signals. As we continue to explore the mysteries of cosmic inflation, we're not just uncovering the origins of the universe, we're also challenging our understanding of time, space, and the very fabric of reality. Next, we'll turn our attention to the multiverse, the idea that our universe might be just one of countless others, each with its own unique set of physical laws and possibilities. Now, let's take a step beyond the boundaries of our own universe and venture into a concept that stretches the limits of our imagination: the multiverse. Imagine, if you will, that our universe is not alone. What if it's just one of countless others, each with its own unique set of physical laws, constants, and even realities? This is the idea behind the multiverse, a theory that suggests our cosmos is part of a much larger, perhaps infinite, collection of universes. The concept of the multiverse arises from several areas of modern physics. One of the most compelling pieces of evidence comes from cosmic inflation, the rapid expansion of the early universe we just discussed. If inflation occurred once, why couldn't it happen multiple times, creating separate bubbles of space-time that evolve into their own distinct universes? Each of these bubbles could have different properties. Some might have stronger gravity, others might have more dimensions, and some might not even support life as we know it. This idea, known as the inflationary multiverse, suggests that our universe is just one bubble in a vast cosmic foam. Another line of thinking comes from quantum mechanics, the branch of physics that deals with the behavior of particles at the smallest scales. According to the many worlds interpretation, every time a quantum event occurs, like the decay of an atom or the spin of an electron, the universe splits into multiple branches. In one branch, the atom decays; in another, it doesn't. Over time, this process could create an infinite number of parallel universes, each representing a different outcome of every possible quantum event. It's a mind-bending idea that suggests every decision you've ever made or didn't make exists in some alternate reality. String theory, a framework that attempts to unify all the forces of nature, also lends support to the multiverse idea. In string theory, the fundamental building blocks of the universe are tiny, vibrating strings. These strings can exist in a vast landscape of possible configurations, each corresponding to a different universe with its own physical laws. This string landscape implies that our universe is just one of many possible solutions to the equations of string theory. But the multiverse isn't just a scientific curiosity, it has profound philosophical implications. If there are infinite universes, does that mean every possible version of reality exists somewhere? Could there be a universe where dinosaurs never went extinct or where humans never evolved? These questions challenge our understanding of existence, purpose, and even the nature of reality itself. Some argue that the multiverse theory makes our universe seem less special, while others see it as a testament to the boundless creativity of the cosmos. Of course, the multiverse remains a highly speculative idea, because these other universes, by definition, lie beyond our observable horizon. They are incredibly difficult, if not impossible, to detect directly. Some scientists are searching for indirect evidence, such as imprints left by collisions between our universe and others in the cosmic microwave background. Others are exploring mathematical models to see if the multiverse can be reconciled with our current understanding of physics. As we ponder the multiverse, we're not just exploring the edges of science, we're also confronting some of the deepest questions about our place in the cosmos. What does it mean to live in a universe that might be just one of many? And if there are infinite realities out there, what does that say about the nature of existence itself? Next, we'll turn our attention to the Higgs field, the invisible force that gives particles their mass and shapes the very fabric of our universe. Now, shifting our focus from the vast possibilities of the multiverse, let's zoom in on something much closer to home, or rather, much closer to the very fabric of reality itself. The Higgs field is an invisible force that permeates all of space, and it plays a crucial role in giving particles their mass. Without it, the universe as we know it simply wouldn't exist. But what exactly is the Higgs field and how does it work? To understand the Higgs field, we need to start with the basics of particle physics. Everything in the universe is made up of tiny particles like electrons and quarks. But here's the mystery. Why do these particles have mass? Why isn't everything just zipping around at the speed of light? The answer lies in the Higgs field, a kind of cosmic molasses that fills the universe. As particles move through this field, they interact with it, and this interaction is what gives them mass. Think of it like wading through water. The more resistance you feel, the more mass you have. Particles that interact strongly with the Higgs field, like the top quark, are heavy, while those that interact weakly, like the electron, are light. The existence of the Higgs field was first proposed in the 1960s by physicist Peter Higgs and others, but it took decades to confirm its existence. The breakthrough came in 2012 at the Large Hadron Collider, the world's most powerful particle accelerator. Scientists there discovered the Higgs boson, a particle that acts as a kind of signature for the Higgs field. Finding the Higgs boson was like finding a ripple in the field, proving that the field itself was real. This discovery was a monumental moment in science, earning Peter Higgs and Francois Englert the Nobel Prize in Physics in 2013. The Higgs field isn't just a neat scientific curiosity, it's a cornerstone of the Standard Model of particle physics, the framework that describes how particles and forces interact. Without the Higgs field, the Standard Model would fall apart. It explains why particles have mass and how the fundamental forces of nature work together. But the Higgs field also raises new questions. For example, why does it have the specific properties it does? And could there be more than one Higgs field, each with its own unique effects? The discovery of the Higgs boson was a triumph, but it also opened the door to even deeper mysteries. Some scientists believe that studying the Higgs field could help us understand dark matter, the mysterious substance that makes up most of the universe's mass. Others think it might hold clues to the unification of all the fundamental forces, a goal that has eluded physicists for decades. The Higgs field is a reminder that even the most fundamental aspects of reality are still full of surprises. As we continue to explore the Higgs field, we're not just learning about particles and forces, we're uncovering the very rules that govern existence. What other secrets does this invisible field hold, and how might it shape our understanding of the universe in the years to come? Next, we'll turn our attention to neutrinos, the elusive particles that pass through matter almost undetected, yet play a vital role in the cosmos. Now, let's step into the shadowy world of neutrinos, particles so elusive they've earned the nickname ghost particles. These tiny, nearly massless entities are everywhere. Trillions of them are passing through your body every second, yet you'd never know it. Neutrinos are so stealthy that they can travel through entire planets without interacting with anything. But why are they so hard to detect, and what makes them so important in our quest to understand the universe? Neutrinos are born in some of the most extreme environments in the cosmos. They are produced in the hearts of stars during nuclear reactions in the Sun and in the explosive deaths of massive stars known as supernova. In fact, when a star goes supernova, it releases an enormous burst of neutrinos, so many that they carry away most of the star's energy. These ghostly particles are the first signal of a supernova, often arriving hours before the light from the explosion reaches us. This makes neutrinos a crucial tool for astronomers, giving them an early warning system to study these cataclysmic events. But detecting neutrinos is no easy task. Because they rarely interact with matter, scientists have to build massive detectors deep underground to shield them from other particles and radiation. One of the most famous neutrino detectors is the Super Kamiok, and in Japan, a giant tank filled with 50,000 tons of ultra-pure water. When a neutrino does interact with the water, it creates a tiny flash of light that sensors can pick up. It's like trying to catch a whisper in a thunderstorm, challenging but not impossible. What makes neutrinos so fascinating is their ability to change forms or flavors as they travel. There are three types of neutrinos: electron neutrinos, muon neutrinos, and tau neutrinos, and they can switch between these flavors as they move through space. This phenomenon, called neutrino oscillation, was a groundbreaking discovery that proved neutrinos have mass, even if it's incredibly small. This discovery shook the foundations of particle physics, as it meant the standard model wasn't complete. Neutrinos were hiding secrets that forced scientists to rethink their understanding of the universe. Beyond their role in supernova, neutrinos could hold the key to some of the universe's biggest mysteries. For example, they might help us understand why the universe is made of matter and not antimatter. In the early moments of the cosmos, matter and antimatter should have been created in equal amounts, annihilating each other and leaving behind nothing but energy. But somehow, matter won out, and neutrinos might have played a role in tipping the scales. Studying neutrinos could also shed light on dark matter, the invisible substance that makes up most of the universe's mass. Some theories suggest that neutrinos and dark matter particles might be connected in ways we're only beginning to explore. As we continue to study these ghostly particles, we're not just uncovering the secrets of neutrinos, we're piecing together the story of the universe itself. From the fiery hearts of stars to the depths of underground detectors, neutrinos are guiding us toward answers to questions we didn't even know to ask. Next, we'll explore another cosmic mystery: gravitational waves, the ripples in space-time that allow us to hear the universe. Now, let's turn our attention to one of the most groundbreaking discoveries in modern physics: gravitational waves. These ripples in the fabric of space-time, first predicted by Albert Einstein over a century ago, were finally detected in 2015, marking a monumental moment in science. Imagine space-time as a vast, invisible ocean. When massive objects like black holes or neutron stars collide, they send out waves across this cosmic ocean, much like ripples spreading across the surface of water. These waves are gravitational waves, and they carry with them the echoes of some of the most violent and energetic events in the universe. For decades, gravitational waves remained elusive, hidden from our detection. Einstein himself doubted we'd ever be able to observe them, given how incredibly faint they are by the time they reach Earth. But thanks to the Laser Interferometer Gravitational Wave Observatory, or LIGO, scientists were able to achieve the impossible. LIGO consists of two massive detectors, one in Louisiana and the other in Washington, each shaped like an enormous L. These detectors use lasers to measure tiny changes in the distance between mirrors, changes so small they're less than the width of a single proton. When a gravitational wave passes through, it stretches and compresses space-time itself, causing these distances to shift ever so slightly. On September 14, 2015, LIGO detected its first gravitational wave, originating from the collision of two black holes over 1 billion light-years away. It was a moment that confirmed Einstein's theory and opened a new window into the cosmos. Gravitational waves are more than just a scientific curiosity. They're a revolutionary tool for observing the universe. Unlike light, which can be blocked or distorted by dust and gas, gravitational waves travel unimpeded, giving us a clear view of events that would otherwise remain hidden. For example, when two black holes spiral toward each other and merge, they emit a burst of gravitational waves that carries information about their masses, spins, and even the shape of space-time around them. These waves allow us to listen to the universe, providing a completely new way to study cosmic phenomena. In 2017, LIGO and its European counterpart, Virgo, detected gravitational waves from the collision of two neutron stars. This event was accompanied by a flash of light, allowing astronomers to observe the same event in both gravitational waves and electromagnetic radiation for the first time. It was like seeing and hearing the universe in harmony, offering unprecedented insights into the nature of these dense stellar remnants. The discovery of gravitational waves has also deepened our understanding of black holes. Before their detection, black holes were largely theoretical objects, inferred from their gravitational effects on surrounding matter. But gravitational waves have given us direct evidence of their existence and allowed us to study their properties in detail. For instance, the waves from black hole mergers reveal how these objects form, evolve, and interact. They've even provided clues about the nature of spacetime itself, testing Einstein's theory of general relativity in extreme conditions. As we continue to refine our ability to detect gravitational waves, the possibilities are endless. Future observatories like the planned Laser Interferometer Space Antenna, or LISA, will be able to detect waves from even more distant and massive sources, such as supermassive black holes at the centers of galaxies. These observations could help us unravel the mysteries of dark matter, dark energy, and the very origins of the universe. Gravitational waves have transformed our understanding of the cosmos, and they're just beginning to reveal their secrets. Next, we'll explore another cosmic enigma, the Great Attractor, a mysterious force pulling galaxies toward it with an irresistible gravitational pull. Now let's journey into one of the most perplexing mysteries of the cosmos, the Great Attractor. Hidden in the depths of space, this enigmatic force exerts a gravitational pull so powerful that it's drawing entire galaxies, including our own Milky Way, toward it at incredible speeds. But what exactly is the Great Attractor, and why has it remained so elusive to scientists? The answer lies in its peculiar location and the challenges it poses to observation. The Great Attractor sits in a region of the sky known as the Zone of Avoidance, an area obscured by the dense plane of our own galaxy. This zone is filled with stars, gas, and dust, making it nearly impossible to observe anything beyond it using traditional optical telescopes. Imagine trying to peer through a thick fog. The light from distant objects is simply blocked or scattered, leaving us blind to what lies on the other side. This is why the Great Attractor has remained shrouded in mystery for so long. Despite its immense gravitational influence, its exact nature and composition are still largely unknown. To overcome this obstacle, scientists have turned to other methods of observation, such as radio and infrared telescopes, which can penetrate the galactic dust and reveal what lies hidden. These tools have allowed researchers to map the motion of galaxies in the region, confirming that something massive, something far beyond the visible, is pulling them in. Current estimates suggest that the Great Attractor has a mass equivalent to tens of thousands of Milky Way galaxies, making it one of the most massive structures in the observable universe. But what could it be? Some theories propose that it's a massive cluster of galaxies, while others suggest it might be part of an even larger structure, like the Shapley supercluster, located even farther away. The Great Attractor isn't just pulling galaxies, it's reshaping our understanding of the universe's large-scale structure. Its existence challenges the idea that matter is evenly distributed across the cosmos, hinting instead at a universe filled with vast, interconnected webs of galaxies and dark matter. This gravitational anomaly also raises questions about the role of dark energy, the mysterious force driving the universe's expansion. Could the Great Attractor be a counterbalance to dark energy, or is it part of a larger cosmic dance we're only beginning to understand? As technology advances, so too does our ability to study this cosmic enigma. Future missions and telescopes, like the James Webb Space Telescope and the Square Kilometre Array, promise to shed more light on the Great Attractor and its surroundings. These tools may finally allow us to pierce through the zone of avoidance and uncover the secrets of this gravitational giant. For now, the Great Attractor remains a tantalizing mystery, a reminder of how much we still have to learn about the forces shaping our universe. Next, we'll delve into another cosmic puzzle, the Fermi paradox, which asks why, in a universe so vast, we seem to be alone. Now, shifting our gaze from the gravitational mysteries of the Great Attractor, we turn to a question that has puzzled scientists and dreamers alike, the Fermi paradox. In a universe so vast, with billions of galaxies and trillions of stars, why haven't we found any signs of extraterrestrial life? This paradox, named after physicist Enrico Fermi, challenges our assumptions about the cosmos and our place within it. The numbers alone seem to suggest that life should be abundant. Our galaxy, the Milky Way, contains hundreds of billions of stars, many of which host planets in the so-called habitable zone, where conditions might support life as we know it. With such staggering odds, it seems almost inevitable that intelligent civilizations should exist elsewhere. Yet, despite decades of searching, we've found no definitive evidence of alien life. Not a single signal, artifact, or trace. So, where is everyone? One possible explanation is that life is far rarer than we think. While the universe may be teeming with planets, the conditions necessary for life to emerge and evolve might be incredibly specific. Perhaps Earth is a cosmic fluke, a rare oasis in a vast desert of lifeless worlds. This idea, known as the rare Earth hypothesis, suggests that the combination of factors needed for complex life-stable stars, the right chemical ingredients, and a long period of planetary stability might be exceedingly uncommon. On the other hand, some scientists propose that intelligent civilizations might exist but are simply too advanced for us to detect. Imagine a civilization millions of years ahead of us in technology. They might communicate in ways we can't yet comprehend or have moved beyond the need for physical exploration. They could be observing us silently, choosing not to reveal themselves. This concept, often referred to as the zoo hypothesis, suggests that advanced civilizations might be intentionally avoiding contact, treating us like a protected species in a cosmic wildlife preserve. Another intriguing possibility is that civilizations might self-destruct before they can make their presence known. The development of advanced technology could come with existential risks such as nuclear war, environmental collapse, or runaway artificial intelligence. If this is a common fate for intelligent species, it might explain why we haven't encountered any. They simply didn't survive long enough to leave a mark on the universe. Then there's the idea that we're looking in the wrong places or the wrong ways. Our current methods of searching for extraterrestrial life, such as scanning for radio signals, might be outdated. Advanced civilizations could be using technologies we haven't even imagined, making their signals invisible to us. Or perhaps life exists in forms so different from our own that we wouldn't recognize it even if we found it. The Fermi paradox isn't just a question about aliens. It's a mirror reflecting our own uncertainties about the universe and our place within it. It challenges us to think critically about the nature of life, intelligence, and the future of our own civilization. As we continue to explore the cosmos, this paradox reminds us that the universe is full of mysteries waiting to be unraveled. Next, we'll explore another profound cosmic mystery, the arrow of time, and why it only moves in one direction. Now, as we ponder the mysteries of the Fermi paradox, let's turn our attention to another profound cosmic enigma, the arrow of time. Unlike the spatial dimensions we can move through freely, time seems to flow in only one direction forward. But why is this the case, and what does it tell us about the universe's evolution? The concept of the arrow of time is deeply tied to a fundamental principle in physics, entropy. Entropy is a measure of disorder in a system, and according to the second law of thermodynamics, it always increases over time. Think of it like this. If you drop a glass and it shatters, the pieces don't spontaneously reassemble into a whole glass. That's because the shattered state has higher entropy, more disorder than the intact glass. This irreversible process gives us a sense of time's direction. We remember the past, not the future, because the past is a state of lower entropy. But why does entropy always increase? The answer lies in the early universe. At the moment of the Big Bang, the universe was in an incredibly ordered, low-entropy state. As it expanded and cooled, entropy began to rise, creating the conditions for stars, galaxies, and eventually life to form. This initial low-entropy state is what sets the direction of time. Without it, time might not have a clear arrow at all. Some theories suggest that the arrow of time might not be as straightforward as it seems. For instance, in the quantum realm, particles can behave in ways that seem to defy our everyday experience of time. Experiments have shown that certain quantum processes can appear to run backward, challenging our understanding of time's flow. Could it be that time's arrow is more flexible than we think, at least on the smallest scales? Another intriguing idea is the possibility of a multiverse, where different universes might have different arrows of time. In some, time could flow backward, while in others it might not flow at all. While this remains speculative, it opens up fascinating questions about the nature of time and its role in the cosmos. The arrow of time isn't just a scientific curiosity, it's a key to understanding the universe's history and future. It shapes everything from the formation of galaxies to the aging of stars and even the way we experience life. As we continue to explore this mystery, we're reminded that time, like the universe itself, is full of surprises waiting to be uncovered. Next, we'll delve into another cosmic relic, the cosmic microwave background, and how it offers us a glimpse into the universe's earliest moments. Now, shifting our gaze to the very beginning of everything, let's explore the cosmic microwave background, often called the universe's oldest photograph. This faint glow, discovered in the 1960s, is the afterglow of the Big Bang, a remnant of the intense heat and energy that filled the cosmos nearly 14 billion years ago. It's like finding a fossil from the dawn of time, offering us a direct glimpse into the universe's infancy. The cosmic microwave background is everywhere, a faint radiation that permeates all of space. It's the cooled-down echo of the universe's fiery birth, now just a few degrees above absolute zero. But don't let its subtle presence fool you. This radiation holds a treasure trove of information. By studying its patterns, scientists have been able to piece together a detailed picture of the early universe, from its density fluctuations to its rate of expansion. One of the most remarkable discoveries from the cosmic microwave background is the evidence it provides for the Big Bang theory itself. The uniformity of this radiation across the sky supports the idea that the universe began as an incredibly hot, dense point and has been expanding ever since. But it's not just a smooth glow. Tiny variations in temperature, less than 1/100th of a degree, reveal the seeds of cosmic structure. These tiny ripples are the blueprints for everything we see today: galaxies, stars, and even planets like Earth. The significance of the cosmic microwave background goes beyond just confirming the Big Bang. It also helps us understand the composition of the universe. By analyzing its properties, scientists have determined that ordinary matter, the stuff we're made of, makes up only about 5% of the cosmos. The rest is dark matter and dark energy, two mysterious forces that continue to shape the universe's evolution. Without this ancient light, we might never have uncovered these profound truths, but the story doesn't end there. The cosmic microwave background also raises new questions. For instance, why does it appear so uniform in all directions, and what caused those tiny fluctuations that eventually grew into galaxies? These puzzles keep scientists digging deeper, using ever more advanced tools to decode the secrets hidden in this ancient light. As we reflect on the cosmic microwave background, we're reminded of how far we've come in understanding the universe's origins. This faint glow, once invisible to us, now serves as a cosmic time capsule, revealing the universe's first moments with stunning clarity. Next, we'll turn our attention to another mysterious force, the vacuum energy, and how it might hold the key to understanding the very fabric of space itself. Now, let's venture into the enigmatic realm of vacuum energy, a concept that challenges our understanding of what it means for space to be empty. At first glance, the vacuum of space might seem like a vast, lifeless void, but in reality, it's teeming with activity. According to quantum mechanics, even in the absence of matter, space is filled with a kind of energy, a subtle, ever-present hum that defies our everyday intuition. This energy, known as vacuum energy, arises from the principles of quantum field theory. In this framework, particles and their corresponding antiparticles constantly pop in and out of existence, creating fleeting fluctuations in the vacuum. These fluctuations aren't just theoretical, they've been observed in experiments like the Casimir effect, where two uncharged metal plates placed close together experience an attractive force due to the energy of the vacuum between them. It's as if the empty space is alive with invisible forces, shaping the behavior of the physical world in ways we're only beginning to understand. But vacuum energy isn't just a curious quirk of quantum mechanics. It might hold the key to one of the greatest mysteries in cosmology, dark energy. Dark energy is the mysterious force driving the accelerated expansion of the universe, and some scientists believe it could be linked to the energy inherent in the vacuum of space. If true, this would mean that the same quantum fluctuations that create vacuum energy on a tiny scale could be influencing the fate of the entire cosmos on a grand scale. However, there's a catch. When scientists calculate the amount of vacuum energy predicted by quantum field theory, the result is staggeringly large, so large, in fact, that it would cause the universe to expand at an unimaginable rate, tearing apart galaxies and stars in an instant. This discrepancy, known as the cosmological constant problem, is one of the biggest unsolved puzzles in physics. Why does the observed value of dark energy seem so much smaller than the theoretical predictions for vacuum energy? Is there a missing piece to this cosmic puzzle, or do we need to rethink our understanding of quantum mechanics and gravity altogether? As we ponder these questions, vacuum energy reminds us that even the emptiest corners of the universe are far from empty. They're alive with potential, brimming with forces that shape the cosmos in ways we're only beginning to unravel. Next, we'll explore another mind-bending concept, the holographic principle, and how it suggests that our universe might be a projection of information encoded on a distant boundary. Now, let's shift our focus to a theory that sounds like it's straight out of science fiction but is deeply rooted in cutting-edge physics, the holographic principle. This mind-bending idea suggests that our universe, with all its vastness and complexity, might actually be a hologram, a projection of information encoded on a distant two-dimensional surface. At first, this might seem impossible, but when we dive into the science, it starts to make a strange kind of sense. The holographic principle emerged from the study of black holes and the nature of information. In the 1970s, physicist Jacob Bekenstein discovered that the amount of information a black hole can contain is proportional to its surface area, not its volume. This was a radical departure from conventional thinking, which assumed information would scale with volume. Later, physicist Leonard Susskind and others expanded on this idea, proposing that the entire universe might operate in a similar way. In other words, all the information needed to describe our three-dimensional reality could be encoded on a two-dimensional boundary, much like a hologram stores a 3D image on a flat surface. But what does this mean for our understanding of reality? If the holographic principle is correct, it challenges the very nature of spacetime. Instead of being a fundamental fabric, spacetime might emerge from something deeper, a network of information encoded at the universe's edges. This idea has profound implications for physics, suggesting that our perception of space and time as continuous and smooth might be an illusion. It also raises questions about the nature of reality itself. Are we living in a universe that's fundamentally informational, where everything we see and experience is a kind of cosmic projection? The holographic principle isn't just a theoretical curiosity. It has practical implications for solving some of the biggest problems in physics. For example, it offers a potential way to reconcile quantum mechanics and general relativity, two theories that describe the universe at vastly different scales but have so far resisted unification. By treating spacetime as emergent rather than fundamental, the holographic principle opens up new avenues for understanding how gravity and quantum particles interact. Of course, this theory is still in its early stages, and much about it remains speculative. But the idea that our universe might be a hologram forces us to rethink everything we thought we knew about reality. It's a reminder that the cosmos is far stranger and more mysterious than we can imagine. As we continue to explore this concept, we'll next turn our attention to another puzzling phenomenon, the pioneer anomaly, and how it challenges our understanding of the laws of physics. Now, let's turn our attention to a mystery that has puzzled scientists for decades, the pioneer anomaly. In the late 1970s, as the Pioneer 10 and Pioneer 11 spacecraft ventured beyond our solar system, something unexpected happened. Both probes began to slow down slightly, deviating from their predicted trajectories. This tiny but consistent deceleration, though seemingly insignificant, sparked a major scientific debate. What was causing these spacecraft to slow down? Was it a flaw in our understanding of physics or something entirely new? At first, scientists considered mundane explanations. One leading theory suggested that thermal radiation heat emitted unevenly from the spacecraft's power sources could be pushing against the probes, creating a tiny but measurable force. This idea seemed plausible, but when researchers crunched the numbers, they found that thermal radiation alone couldn't fully account for the anomaly. The mystery deepened, and the scientific community began to wonder if something more profound was at play. Could the pioneer anomaly be evidence of new physics? Some theorists propose that it might hint at modifications to Einstein's theory of general relativity, or even the existence of unknown forces acting on the spacecraft. Others speculated about the influence of dark matter or dark energy, those elusive cosmic components that still defy our understanding. The anomaly became a tantalizing puzzle, one that challenged our grasp of the fundamental laws governing the universe. Despite decades of investigation, the pioneer anomaly remains unsolved. While some researchers believe the thermal radiation explanation is the most likely, others argue that the data still doesn't fully align with this theory. The lack of a definitive answer keeps the mystery alive, reminding us that even in the age of advanced space exploration, the cosmos still holds secrets we've yet to uncover. The pioneer anomaly serves as a humbling reminder of how much we still have to learn about the universe. It's a testament to the fact that even the smallest discrepancies can lead to groundbreaking questions, pushing the boundaries of our knowledge. As we continue to explore the cosmos, anomalies like this one challenge us to think bigger, dig deeper, and remain open to the possibility that the universe is far more complex than we've ever imagined. Next, we'll journey to the outer edges of our solar system, where the Kuiper belt and Oort cloud hold clues to the origins of our cosmic neighborhood. What secrets do these distant regions hide, and how do they shape our understanding of the universe? Let's find out. Now, let's venture beyond the familiar planets and moons of our solar system, to the distant and enigmatic realms of the Kuiper belt and the Oort cloud. These icy, far-flung regions mark the outer edges of our cosmic neighborhood, and they hold secrets that could rewrite our understanding of the solar system's origins. The Kuiper belt, a vast ring of icy bodies beyond Neptune, is home to dwarf planets like Pluto and countless smaller objects. Think of it as a cosmic freezer, preserving remnants from the early days of the solar system. These frozen relics are like time capsules, offering clues about the conditions and materials that existed over 4.5 billion years ago. Comets, those dazzling visitors that occasionally streak across our skies, often originate here. When a comet's orbit is disturbed, it can be flung inward, bringing with it ancient ice and dust that have remained unchanged since the solar system's infancy. Studying these comets helps scientists piece together the story of how planets formed and evolved. But the Kuiper belt is just the beginning. Beyond it lies the Oort cloud, a spherical shell of icy objects that stretches nearly a light year from the Sun. This distant region is so vast and faint that it's never been directly observed, but its existence is inferred from the long-period comets that occasionally visit the inner solar system. These comets, with orbits that can take thousands or even millions of years, are thought to originate in the Oort cloud. Unlike the Kuiper belt, which lies in a relatively flat plane, the Oort cloud surrounds the solar system like a cosmic bubble, hinting at a chaotic and dynamic past. What makes these regions so fascinating is their potential to reveal the solar system's early history. The Kuiper belt and Oort cloud are thought to be leftovers from the protoplanetary disk, the swirling cloud of gas and dust that gave birth to the Sun and planets. By studying the composition and orbits of objects in these regions, scientists can gain insights into the processes that shaped our cosmic home. For example, the presence of certain chemicals in comets could tell us about the conditions in the early solar system, and even the origins of water and organic molecules on Earth. Yet, despite their importance, these regions remain largely unexplored. Missions like New Horizons, which flew past Pluto in 2015, have given us a glimpse of the Kuiper belt, but much of it remains uncharted. The Oort cloud, on the other hand, is so distant that sending a probe there would take tens of thousands of years with current technology. This makes it one of the most mysterious and tantalizing frontiers in our solar system. The Kuiper belt and Oort cloud remind us that the solar system is far more than just the Sun and its planets. These icy realms are a testament to the complexity and beauty of our cosmic neighborhood, and they challenge us to keep exploring, keep questioning, and keep pushing the boundaries of what we know. As we turn our gaze to the next mystery, we'll explore a concept that could explain why we haven't found extraterrestrial life despite the vastness of the universe. What is the Great Filter, and what does it mean for humanity's future? Let's dive in. Now, shifting our focus from the icy frontiers of our solar system, let's explore a concept that could hold the key to one of the universe's greatest mysteries, the Great Filter. This idea attempts to answer a haunting question: why, in a cosmos teeming with billions of stars and planets, have we found no trace of extraterrestrial civilizations? The Great Filter suggests that there's some kind of barrier, a critical challenge or event, that prevents life from advancing to the point of becoming a spacefaring civilization. But where does this filter lie? Is it behind us in our past or ahead of us in our future? And what does it mean for humanity's survival? To understand the Great Filter, we need to consider the steps required for a civilization to emerge and thrive. First, life must arise from non-living matter, a process we still don't fully understand. Then, that life must evolve into complex, intelligent beings capable of creating technology. Finally, those beings must survive long enough to explore and colonize the stars. The Great Filter could be any one of these steps, or perhaps even a combination of them. If the filter lies in our past, it means we've already overcome an incredibly rare and difficult hurdle, such as the emergence of life itself or the evolution of intelligence. This would explain why we haven't found other civilizations. They might have never made it this far, but what if the Great Filter is still ahead of us? This is the more unsettling possibility. It could mean that civilizations like ours inevitably face a catastrophic event, nuclear war, climate collapse, or some other existential threat that wipes them out before they can spread beyond their home planet. If this is the case, humanity's future could be far more precarious than we realize. The absence of alien civilizations might not be a sign of their rarity, but rather a grim warning of what awaits us. The implications of the Great Filter are profound. If it's behind us, we might be one of the few, or even the only, intelligent species in the universe. This would make our survival and exploration of the cosmos all the more important. But if the filter lies ahead, it becomes a race against time to identify and overcome the challenges that could doom us. Either way, the Great Filter forces us to confront the fragility of life and the responsibility we have to safeguard our future. As we ponder this concept, it's worth considering how we might detect signs of the Great Filter. Are there clues in the fossil record or in the ruins of ancient civilizations on Earth? Could we find evidence of past life on Mars or other planets that failed to thrive? And what steps can we take now to ensure that humanity doesn't become another casualty of this cosmic barrier? The Great Filter isn't just a theoretical idea, it's a call to action, urging us to think deeply about our place in the universe and the choices we make as a species. With this thought-provoking concept in mind, let's turn our attention to another cosmic mystery, the axis of evil. What is this strange alignment in the cosmic microwave background, and why does it challenge our understanding of the universe's structure? Let's find out. Now, let's venture into one of the most perplexing cosmic mysteries that has left scientists scratching their heads, the axis of evil. This isn't a sinister plot from a sci-fi movie. It's a real, unexplained pattern in the cosmic microwave background, or CMB, which is the faint afterglow of the Big Bang. The CMB is like a snapshot of the universe when it was just a baby, and studying it helps us understand how the cosmos evolved. But here's the twist. The CMB shows strange, large-scale alignments that shouldn't exist according to our current understanding of physics. These anomalies seem to form a kind of axis, and they've been dubbed the axis of evil because they challenge everything we thought we knew about the universe's structure. So, what exactly is this axis of evil? Imagine looking at a map of the CMB and noticing that certain temperature fluctuations, tiny variations in the heat left over from the Big Bang aren't randomly distributed. Instead, they appear to align along a specific direction, almost as if the universe has a preferred orientation. This is a big deal because the standard model of cosmology assumes that the universe is isotropic, meaning it should look the same in all directions. The axis of evil throws a wrench into this assumption, suggesting that there might be something fundamentally wrong with our understanding of the cosmos. One possible explanation is that these anomalies are just a fluke, a statistical coincidence that doesn't mean much in the grand scheme of things. But the odds of such a pattern occurring by chance are incredibly low, which has led some scientists to propose more radical ideas. Could the axis of evil be evidence of a pre-Big Bang universe, a remnant of some earlier cosmic structure that influenced the birth of our universe? Or does it hint at the existence of a multiverse, where our universe is just one of many, each with its own unique properties? These are questions that push the boundaries of our knowledge and force us to rethink the very foundations of cosmology. The implications of the axis of evil are profound. If it's real and not just a quirk of the data, it could mean that our universe isn't as uniform as we thought. This could have ripple effects on everything from the way galaxies form to the fate of the cosmos itself. For example, if the universe has a preferred direction, it might affect how dark energy behaves or how gravity operates on the largest scales. It could even challenge Einstein's theory of general relativity, which assumes that the laws of physics are the same everywhere. But here's the catch: the axis of evil is still a mystery. Despite decades of research, scientists haven't been able to fully explain it. Some argue that it's an artifact of how we process the CMB data, while others believe it's a genuine cosmic anomaly waiting to be understood. Either way, it's a reminder that the universe is full of surprises, and there's still so much we don't know. As we grapple with the enigma of the axis of evil, it's worth reflecting on what it means for our quest to understand the cosmos. Are we on the brink of a major breakthrough, or are we just scratching the surface of a much deeper mystery? Whatever the answer, one thing is clear: the universe is far more complex and mysterious than we ever imagined. And with that, let's turn our attention to another cosmic oddity, the Eridanus supervoid. What is this vast, empty region of space, and why does it defy our expectations? Let's dive in. Now, let's shift our gaze to another cosmic puzzle that has left astronomers both fascinated and baffled: the Eridanus supervoid. Picture this: a colossal region of space stretching over hundreds of millions of light years where there's almost nothing. No galaxies, no stars, not even much dark matter. It's like a giant, empty bubble in the fabric of the universe, and it's one of the largest structures ever discovered. But what makes the Eridanus supervoid so intriguing isn't just its size or emptiness, it's the way it seems to defy our expectations about how the universe should behave. The Eridanus supervoid was first noticed when scientists were studying the cosmic microwave background, or CMB, the faint afterglow of the Big Bang. They found a peculiar cold spot in the CMB, a region where the temperature was slightly lower than the surrounding areas. At first, this might not sound like a big deal, but when they looked closer, they realized this cold spot aligned with the Eridanus supervoid. This raised a tantalizing question: could the void be causing the cold spot? And if so, how? One theory suggests that the supervoid's emptiness might be affecting the light traveling through it. As photons from the CMB pass through the void, they lose a tiny bit of energy due to a phenomenon called the integrated Sachs-Wolf effect. This energy loss could explain why the CMB appears colder in that region. But here's the catch: the Eridanus supervoid is so vast that its effect on the CMB should be much smaller than what we're observing. This discrepancy has led some scientists to wonder if there's more to the story. Could the supervoid be interacting with dark energy in some unexpected way? Or is there another, even more mysterious force at play? The implications of the Eridanus supervoid go beyond just the CMB. If it's truly influencing the expansion of the universe, it could challenge our understanding of dark energy, the mysterious force driving the cosmos apart. Dark energy is already one of the biggest mysteries in physics, and if the supervoid is altering its behavior, it could mean we're missing a crucial piece of the puzzle. Some researchers have even speculated that the supervoid might be a window into a deeper layer of reality, hinting at new physics that we haven't yet discovered. But as with many cosmic mysteries, the Eridanus supervoid isn't without its skeptics. Some argue that the cold spot in the CMB might just be a statistical fluke, a random fluctuation that doesn't require a supervoid to explain. Others suggest that our current models of the universe might not be accurate enough to fully understand what's happening. Either way, the Eridanus supervoid remains a tantalizing enigma, one that pushes us to rethink our assumptions about the cosmos. As we ponder the mysteries of the Eridanus supervoid, it's a reminder that the universe is full of surprises. From the tiniest particles to the largest structures, there's always something new to discover, something that challenges our understanding and forces us to ask deeper questions. And with that, let's turn our attention to another mind-bending concept, the Planck scale. What happens when we zoom in to the smallest possible level of reality? Let's explore. Now, let's zoom way in to the very fabric of reality itself. Imagine trying to measure something so small that it's beyond the reach of even our most advanced technology. This is the Planck scale, the smallest possible level of existence in the universe. Named after physicist Max Planck, this scale represents the limits of our understanding, where the rules of classical physics break down and quantum gravity takes over. At this level, space and time cease to behave in ways we're familiar with, and the very nature of reality becomes a blur of uncertainty. The Planck scale is defined by three fundamental constants: the speed of light, Planck's constant, and the gravitational constant. Together, they give us the Planck length, which is about 1.6 times 10 to the power of -35 meters. To put that into perspective, if you were to magnify an atom to the size of the observable universe, the Planck length would still be smaller than a single atom within that universe. It's almost impossible to grasp just how tiny this scale is, but it's here, at this unimaginably small level, that the universe reveals its most fundamental secrets. At the Planck scale, the smooth, continuous fabric of spacetime we're used to dissolves into a frothy, chaotic sea of quantum fluctuations. This is where quantum gravity comes into play, attempting to reconcile the two great pillars of modern physics: quantum mechanics and general relativity. Quantum mechanics governs the behavior of particles at the smallest scales, while general relativity describes the force of gravity on cosmic scales. But when you try to combine them at the Planck scale, the math breaks down and our current theories fail. This is one of the biggest challenges in physics, finding a theory of quantum gravity that can explain what happens in this extreme realm. One of the leading candidates for such a theory is string theory, which suggests that the fundamental building blocks of the universe aren't particles but tiny, vibrating strings. At the Planck scale, these strings would be the smallest entities, and their vibrations would give rise to all the particles and forces we observe. But string theory is still just that, a theory. Testing it experimentally is nearly impossible because the Planck scale is so far beyond what we can currently probe. Even the most powerful particle accelerators, like the Large Hadron Collider, can't reach energies high enough to explore this domain. Another challenge is that at the Planck scale, the very concept of space and time becomes fuzzy. Some theories suggest that space-time might be made up of discrete, indivisible units like pixels on a screen. Others propose that time itself might not exist at this level, or that it might flow in ways we can't comprehend. These ideas push the boundaries of our imagination and force us to rethink what we know about the universe. The Planck scale isn't just a theoretical curiosity, it's a frontier of discovery. Understanding what happens at this level could unlock the secrets of black holes, the Big Bang, and even the nature of reality itself. But for now, it remains a tantalizing mystery, a reminder that the universe still holds countless secrets waiting to be uncovered. And as we ponder the Planck scale, we're reminded that sometimes the smallest things can lead to the biggest questions. With that, let's turn our attention to another cosmic enigma, the Boltzmann brain. What if the universe could spontaneously create consciousness? Let's explore. Now, let's venture into one of the strangest and most mind-bending ideas in cosmology, the Boltzmann brain. Imagine for a moment that somewhere in the vast emptiness of space, a fully formed, self-aware brain could spontaneously pop into existence. Not attached to a body, not part of a living being, but just a brain, complete with memories, thoughts, and a sense of self. This is the essence of the Boltzmann brain thought experiment, a concept that challenges our understanding of reality, consciousness, and the very nature of the universe. The idea stems from the work of physicist Ludwig Boltzmann, who explored the statistical nature of entropy and the second law of thermodynamics. In simple terms, entropy is a measure of disorder in a system, and the second law states that entropy tends to increase over time. But Boltzmann also realized that, given enough time, random fluctuations could lead to highly ordered states like a brain arising spontaneously from chaos. In an infinite universe where time stretches endlessly, the probability of such a fluctuation becomes not just possible but inevitable. So, what does this mean for us? If Boltzmann brains are possible, then the odds suggest that there are far more of them in the universe than there are ordinary, biological brains like ours. This raises a startling question. How do we know we're not Boltzmann brains ourselves? After all, if a brain can spontaneously form with a complete set of memories and experiences, how can we be sure that our own sense of reality isn't just a fleeting, random fluctuation? This thought experiment isn't just a quirky puzzle, it has profound implications for cosmology. If the universe is infinite and eternal, as some theories suggest, then Boltzmann brains become a statistical inevitability. But this creates a paradox. If Boltzmann brains are more likely than ordinary observers, why do we perceive a stable, ordered universe? Some scientists argue that this paradox points to flaws in our understanding of the cosmos, suggesting that our current models might be missing something fundamental. The Boltzmann brain also ties into questions about consciousness. If a brain can arise spontaneously, complete with a sense of self, what does that say about the nature of consciousness? Is it merely a byproduct of physical processes, or does it hint at something deeper, something intrinsic to the fabric of reality? These questions blur the line between science and philosophy, pushing us to rethink what it means to exist. While the Boltzmann brain remains a theoretical concept, it serves as a powerful reminder of how strange and mysterious the universe can be. It challenges us to question our assumptions, to explore the boundaries of what we know, and to remain open to the possibility that reality might be far stranger than we can imagine. And as we ponder this bizarre idea, we're reminded that the universe is full of questions waiting to be answered, and sometimes the answers might be as strange as the questions themselves. With that, let's turn our attention to another cosmic mystery, the simulation hypothesis. Could our universe be nothing more than a highly advanced simulation? Let's dive in. Now, let's shift our focus to one of the most provocative ideas in modern science and philosophy, the simulation hypothesis. What if everything we see, touch, and experience our entire universe is nothing more than an incredibly advanced simulation? This idea, once relegated to the realm of science fiction, has gained serious traction among scientists, philosophers, and even tech entrepreneurs. But what exactly is the simulation hypothesis, and why does it captivate so many minds? At its core, the simulation hypothesis suggests that our reality might be an artificial construct created by a highly advanced civilization. Think of it like a video game, but on a cosmic scale. In this scenario, every star, every planet, and every living being could be part of a vast, intricate simulation running on some unimaginably powerful computer. The idea isn't entirely new. Philosophers like René Descartes pondered similar questions centuries ago, but modern technology has given it a fresh perspective. One of the most compelling arguments for the simulation hypothesis comes from the rapid advancement of computing power. Over the past few decades, we've seen virtual reality and artificial intelligence evolve at an astonishing pace. If this trend continues, it's not hard to imagine a future where civilizations could create simulations indistinguishable from reality. And if such a civilization exists, why wouldn't they run countless simulations, each with its own set of rules and inhabitants? In this scenario, the odds of us being in the base reality, the original, non-simulated universe, become vanishingly small. But the simulation hypothesis isn't just about technology, it's also rooted in physics. Some scientists point to the strange, almost mathematical nature of the universe as evidence. For example, the laws of physics seem to follow precise, elegant equations, almost as if they were programmed. Quantum mechanics, with its probabilistic nature and observer-dependent outcomes, has also been interpreted by some as a potential glitch or feature of a simulated reality. Could these phenomena be hints that we're living in a digital construct? Of course, the simulation hypothesis isn't without its critics. Many argue that it's untestable and therefore falls outside the realm of science. After all, how could we ever prove that we're in a simulation if the simulation is designed to be indistinguishable from reality? Others point out that the idea raises more questions than it answers. Who created the simulation, why, and what happens if we ever figure out the truth? These questions blur the line between science and philosophy, making the simulation hypothesis as much a thought experiment as a scientific theory. Despite the skepticism, the idea continues to spark debate and inspire research. Some scientists have even proposed ways to test the hypothesis, such as looking for pixelation in the fabric of space-time or searching for computational limits in the universe's behavior. While these efforts are still in their infancy, they highlight the growing interest in exploring the boundaries of reality. The simulation hypothesis also forces us to confront profound questions about existence, consciousness, and the nature of reality. If we are living in a simulation, what does that mean for free will, morality, and the purpose of life? Are we merely characters in someone else's story, or do we have the power to shape our own destiny within the simulation? These questions challenge us to rethink our place in the cosmos and to consider the possibility that reality might be far more complex and far stranger than we ever imagined. As we ponder these mind-bending ideas, we're reminded that the universe is full of mysteries waiting to be unraveled. Whether or not the simulation hypothesis holds water, it serves as a powerful reminder to question our assumptions and to remain open to the possibility that reality might be far more extraordinary than we can comprehend. And with that, let's turn our attention to another cosmic mystery, the ultimate fate of the universe. Will it end in a fiery collapse or a cold, dark expanse? Let's explore the possibilities. Now, let's journey into one of the most profound questions about the cosmos, the ultimate fate of the universe. Will it end in a dramatic collapse or a slow, cold fade into darkness? This brings us to the two leading theories, the Big Crunch and the Big Freeze, each painting a vastly different picture of how the universe might meet its end. The Big Crunch scenario suggests that the universe, which has been expanding since the Big Bang, could one day reverse course. Imagine all the galaxies, stars, and planets being pulled back together by gravity, collapsing into a single point, a singularity. This would be like hitting the rewind button on the universe's expansion, leading to a fiery, chaotic end. The driving force behind this scenario is gravity, the same force that keeps planets in orbit and galaxies together. If the density of matter in the universe is high enough, gravity could eventually overcome the expansion, causing everything to collapse inward. It's a dramatic and almost poetic vision of the universe's end, where everything that ever existed would be compressed into an unimaginably dense point. On the other hand, the Big Freeze presents a far colder and lonelier fate. In this scenario, the universe continues to expand forever, driven by dark energy, the mysterious force we discussed earlier. As galaxies move farther apart, stars burn out, and black holes evaporate, the universe would gradually cool down, becoming a vast, dark, and empty expanse. This is sometimes called the heat death of the universe, where all energy is evenly distributed and no work can be done. It's a slow, quiet end where the universe fades into a state of maximum entropy with no light, no heat, and no life. So, what determines which of these fates awaits us? It all comes down to the balance between gravity and dark energy. If gravity is strong enough to counteract the expansion, we're headed for the Big Crunch. But if dark energy continues to dominate, pushing galaxies apart faster and faster, the Big Freeze becomes inevitable. Current observations suggest that dark energy is winning the battle, making the Big Freeze the more likely outcome. However, the universe is full of surprises, and our understanding of these forces is still evolving. These two scenarios aren't just scientific theories, they're also deeply philosophical. The Big Crunch suggests a cyclical universe where the end could be the beginning of a new cosmic cycle. The Big Freeze, on the other hand, implies a linear, one-way journey toward an eternal stillness. Both ideas challenge us to think about the nature of time, existence, and the ultimate destiny of everything we know. As we contemplate these cosmic possibilities, we're reminded of how much we still have to learn about the universe. Whether it ends in fire or ice, the story of the cosmos is far from over. And with that, let's turn our attention to the final mysterious force on our list, the role of consciousness in shaping reality. Could our minds hold the key to understanding the universe itself? Let's explore this fascinating idea next. Now, let's venture into one of the most intriguing and debated ideas in modern science and philosophy, the role of consciousness in shaping reality. Could it be that our minds are not just passive observers of the universe but active participants in its very fabric? This idea, while controversial, has sparked fascinating discussions across disciplines from quantum mechanics to metaphysics. At the heart of this concept is the idea that consciousness might influence the behavior of particles at the quantum level. One of the most famous experiments supporting this idea is the double-slit experiment. In this experiment, particles like electrons behave differently when observed. When no one is watching, they act like waves, creating an interference pattern. But when observed, they behave like particles, as if the act of observation itself changes their nature. This has led some scientists and philosophers to suggest that consciousness might play a role in collapsing the wave function, essentially determining the state of reality. But what does this mean for our understanding of the universe? If consciousness can influence quantum systems, it raises profound questions about the nature of reality itself. Are we, as conscious beings, co-creators of the universe, or is consciousness simply a byproduct of physical processes with no real influence on the world around us? These questions sit at the intersection of science and philosophy, challenging us to rethink our place in the cosmos. Some theories go even further, suggesting that consciousness might be a fundamental aspect of the universe, much like space and time. This idea, known as panpsychism, proposes that all matter has some form of consciousness, no matter how rudimentary. While this might sound like science fiction, it's a serious area of study for some physicists and philosophers. If true, it would mean that consciousness is woven into the very fabric of reality, shaping the universe in ways we're only beginning to understand. Of course, these ideas are far from settled. Critics argue that there's no concrete evidence linking consciousness to quantum mechanics, and that the double-slit experiment can be explained without invoking the observer's mind. They point out that the act of measurement, not consciousness, is what collapses the wave function. Still, the debate continues, with new experiments and theories emerging all the time. What's clear is that the role of consciousness in the universe is one of the most profound mysteries we face. Whether it's a fundamental force or an emergent property, consciousness challenges us to think deeply about the nature of reality and our place within it. As we continue to explore this fascinating topic, we're reminded that the universe is not just a collection of physical laws, it's a place where mind and matter might be deeply intertwined. With that, let's take a closer look at one of the most puzzling aspects of this idea, the observer effect. How does the act of observation influence quantum systems, and what does it tell us about the nature of reality? Let's dive deeper into this mystery next. Now, let's take a closer look at the fascinating connection between consciousness and quantum mechanics. This relationship has sparked some of the most intriguing debates in science, challenging our understanding of reality itself. At the core of this discussion is the double-slit experiment, a cornerstone of quantum physics that continues to baffle and inspire researchers. In the double-slit experiment, particles such as electrons are fired at a barrier with two slits. When no one observes the particles, they behave like waves, creating an interference pattern on the screen behind the barrier. But when an observer measures which slit the particle goes through, it suddenly behaves like a single particle, as if the act of observation changes its nature. This phenomenon has led some to propose that consciousness might play a role in determining the outcome of quantum events. But how does this work? One interpretation is that the observer's consciousness collapses the wave function, the mathematical description of a particle's possible states. In other words, the act of observing forces the particle to choose a specific state, transitioning from a cloud of possibilities to a definite reality. This idea suggests that consciousness isn't just a passive observer but an active participant in shaping the universe. However, not everyone agrees with this interpretation. Critics argue that it's not consciousness itself but the act of measurement, such as the interaction between the particle and the measuring device, that causes the wave function to collapse. They point out that the observer's mind isn't necessary for this process to occur. Instead, it's the physical interaction that matters, not the awareness of it. Despite the controversy, the double-slit experiment has opened the door to profound questions about the nature of reality. Could it be that the universe exists in a state of potential until observed? And if so, what does that mean for the role of consciousness in the cosmos? Some theories even suggest that consciousness might be a fundamental aspect of the universe, as essential as space and time. This idea, while speculative, challenges us to rethink our understanding of existence. As we explore these questions, it's important to remember that the relationship between consciousness and quantum mechanics is still a mystery. While experiments like the double-slit experiment provide tantalizing clues, they don't yet offer definitive answers. What they do offer, however, is a glimpse into the profound interconnectedness of mind and matter, inviting us to consider the possibility that the universe is far stranger and more wondrous than we ever imagined. With that in mind, let's turn our attention to another intriguing aspect of this mystery, the observer effect. How does the act of observation influence quantum systems, and what does it reveal about the nature of reality? Let's explore this next. Now, let's dive deeper into the observer effect, a phenomenon that continues to challenge our understanding of reality. At its core, the observer effect suggests that the act of measuring or observing a quantum system can fundamentally alter its behavior. This isn't just a quirk of quantum mechanics, it's a profound insight into how the universe operates at its most fundamental level. Take, for example, the famous double-slit experiment we just discussed. When particles like electrons are observed, they behave differently than when they're left unobserved. Without observation, they act like waves, creating an interference pattern. But the moment we try to measure which slit they pass through, they switch to behaving like particles. This shift raises a critical question. Is it the presence of an observer, or perhaps consciousness itself, that causes this change? Or is it simply the physical interaction of measurement that disrupts the system? This question has sparked intense debate among scientists and philosophers. Some argue that the observer effect points to a universe where consciousness plays an active role in shaping reality. In this view, the act of observation isn't just passive, it's a creative force that collapses the wave function, turning possibilities into definite outcomes. This idea, while controversial, suggests that the universe might not exist in a fixed state until it's observed. On the other hand, many physicists propose a more pragmatic explanation. They argue that the observer effect isn't about consciousness at all, but rather the unavoidable disturbance caused by the tools we use to measure quantum systems. For instance, shining light on an electron to observe it changes its momentum, altering its behavior. In this interpretation, the observer effect is a consequence of the physical limitations of measurement, not a mystical interaction between mind and matter. Regardless of the interpretation, the observer effect has far-reaching implications. It challenges the classical notion of an objective reality, where things exist independently of observation. Instead, it suggests that reality might be more fluid, shaped in part by how we interact with it. This idea has influenced fields beyond physics, including philosophy, where it raises questions about the nature of existence and the limits of human knowledge. From a scientific perspective, the observer effect also highlights the challenges of studying quantum systems. It reminds us that the tools we use to explore the universe can sometimes change the very things we're trying to understand. This has led to the development of new techniques like quantum non-demolition measurements, which aim to minimize the impact of observation on the system being studied. As we reflect on the observer effect, it's clear that this phenomenon is more than just a scientific curiosity. It's a gateway to deeper questions about the nature of reality. Whether it's the role of consciousness, the limits of measurement, or the very fabric of existence, the observer effect invites us to rethink our assumptions about the universe. And as we continue to explore these mysteries, one thing is certain: the universe is far more intricate and interconnected than we ever imagined. With this in mind, let's turn our attention to another profound mystery: the hard problem of consciousness. What makes consciousness so difficult to explain, and how might it be connected to the fundamental forces of the universe? Let's explore this next. Now, let's shift our focus to one of the most perplexing questions in science: the hard problem of consciousness. What exactly is consciousness, and why is it so difficult to explain? Unlike other scientific challenges, consciousness isn't just about understanding how the brain works, it's about explaining why and how we experience the world at all. This is what philosopher David Chalmers famously called the hard problem, and it remains one of the most debated topics in both science and philosophy. At its core, the hard problem asks why physical processes in the brain give rise to subjective experiences. Think about it. We can map neurons, study brain activity, and even predict behavior, but none of that fully explains why we feel emotions, see colors, or have a sense of self. It's as if there's a gap between the physical world and our inner experiences, and bridging that gap has proven to be incredibly challenging. One intriguing theory that attempts to address this mystery is panpsychism. Unlike traditional views that see consciousness as emerging from complex brain functions, panpsychism suggests that consciousness might be a fundamental property of the universe, much like space, time, or mass. In this view, even the smallest particles might have some form of basic awareness, and complex consciousness arises when these tiny bits of awareness combine in sophisticated ways. While this idea might sound far-fetched, it offers a radical way to think about the relationship between mind and matter. Another perspective comes from integrated information theory, which proposes that consciousness arises from the way information is processed and integrated in a system. According to this theory, any system with a high degree of integrated information, whether it's a human brain or, hypothetically, a sufficiently advanced computer, could possess consciousness. This approach shifts the focus from the physical substrate to the patterns of information flow, offering a new way to explore the nature of awareness. But why does consciousness matter when we're talking about the universe? Some scientists and philosophers argue that consciousness might not just be a byproduct of the universe, it could play an active role in shaping it. This idea ties back to the observer effect we discussed earlier, where the act of observation seems to influence quantum systems. Could consciousness itself be a fundamental force, interacting with the fabric of reality in ways we don't yet understand? It's a bold idea, and while it's far from proven, it opens up fascinating possibilities about the interconnectedness of mind and cosmos. The hard problem of consciousness also raises profound questions about the nature of existence. If consciousness is fundamental, does that mean the universe itself has some form of awareness? Could the cosmos be experiencing itself through us? These questions might sound like science fiction, but they're grounded in serious scientific and philosophical inquiry. And while we don't have definitive answers yet, the very act of asking these questions pushes the boundaries of what we know. As we continue to explore the mysteries of consciousness, one thing is clear: it's not just a problem for neuroscientists or philosophers, it's a challenge that touches on the very essence of what it means to exist. Whether consciousness is a fundamental property of the universe, an emergent phenomenon, or something else entirely, it remains one of the most profound mysteries we've ever encountered. And as we grapple with these questions, we're reminded once again that the universe is far more mysterious and interconnected than we ever imagined. With that in mind, let's turn our attention to another cosmic enigma, the ultimate fate of the universe. Will it end in a big crunch, a big freeze, or something entirely different? Let's explore this next, as we reach the end of our journey through the 25 mysterious forces shaping the universe. It's impossible not to feel a sense of awe at just how much we still have to uncover. From the invisible grip of dark matter holding galaxies together to the mind-bending possibilities of the multiverse, each force we've explored reveals a universe that is far more complex and interconnected than we ever imagined. These mysteries don't just challenge our understanding, they inspire us to keep asking questions, to keep searching for answers, and to keep pushing the boundaries of what we know. Think about it, every discovery we make, from the detection of gravitational waves to the exploration of quantum entanglement, peels back another layer of the cosmic onion. Yet with each layer, we find more questions waiting to be answered. What lies beyond the observable universe? Could there be other dimensions we've yet to detect? And what role does consciousness play in the grand scheme of things? These are the kinds of questions that drive scientists, philosophers, and curious minds like you to keep exploring. The beauty of these mysteries is that they remind us how much we still have to learn. They show us that the universe is not just a collection of stars and planets, but a dynamic, ever-evolving system governed by forces we're only beginning to understand. And while we may not have all the answers yet, the journey of discovery is just as thrilling as the destination. So, what do you think? Which of these cosmic forces fascinates you the most? Do you believe we'll ever fully unravel the mysteries of dark energy, or will the multiverse remain forever out of reach? Share your thoughts in the comments below. I'd love to hear your ideas and theories. And if you've enjoyed this deep dive into the mysteries of the universe, don't forget to hit that like button, subscribe, and ring the notification bell so you never miss out on our next cosmic adventure. Together, let's keep exploring the wonders of the cosmos and uncovering the secrets that lie hidden in the stars. Until next time, stay curious.